Okay. So, a little bit of a fun 2-day adventure there. Perfect timing to throw a wrench into everything. So, but that's all right. We'll adjust as we go along. I guess what else can we really do at this point? But we're here again, and we'll just keep moving forward, and hopefully everyone's kind of seen the announcements at this point. Right? I've been recording these for a while. I've been posting these for a while. So in case you guys can't make it in, then the recording will be online there for you. You guys can just keep up with it as it is, right? And as a fringe benefit, if you guys ever have trouble sleeping, then you have hours of me roaming on. It'll put you right. It'll put you right out, or make you violently angry. I don't know, one or the other, right? Or maybe both. But we're here and we're making it. What it is. But anyway, before we launch back into it, let's get started with prayer, and then we'll continue on. And so, Lord, we just thank you for another blessing of another day, Lord. We just thank you for another opportunity that we have to get up and to go and just to see the world around us, Lord, and the gift and the beauty that you've put into it, Lord. We just pray this, help us to never take that for granted. Help us to always have our eyes open and looking for you, Lord, wherever you might be in our days, Lord. We pray that you just make yourself known to us. We pray that you just open our hearts to see what you would have us see today, Lord. And just open our ears and our eyes to the people around us and how we can reflect you to them. We just pray this in your name. Amen. All right. So, a couple of one quick note. Don't worry about it. Anyway, we'll deal with that if it comes up. But
that's not comforting.
No. It's not. Yeah. What's up? No. You guys got a nice day off. So yeah, that is a benefit. What's up?
I have to do your hand.
Yeah, my bicycle and I had a fight with the asphalt in the asphalt one. So yeah, I almost took it out, but at the end it kind of got to me.
You'll get it next time, though.
I hope there's not a next time. We'll see. But anyway, so we were making our way through chapter 6, and 6, 7, or 8 are pretty closely linked together. We're basically going to build an atom, and then we're going to build molecules from them. The two big parts of chapter 6 are just dealing with the energy levels of the atoms or the electrons, and that was kind of that first part there where we had to deal with transitions and light and emission and all that kind of stuff. So that's just kind of an exercise in mathematics. And then from there we move into the more conceptual side for the next couple of chapters, where we just simply deal with how atoms or the conceptual side of building an atom, and then bringing them together to draw structures, is what it is. And one of these tricky topics that we run into is the idea of quantum numbers. And I think even, doing what I do when I go through and read some of these general chemistry textbooks, they still find ways to make them, I think, more confusing than they need to be. And I'm not saying that they're wrong or that it's not a good description. It just doesn't, for me, it doesn't quite click, right? And so I say all this just to kind of make sure that you guys are kind of paying attention and trying to understand what it is. Like, this is going to be one of those topics that you guys are going to look at and say, I have no idea where in the world we even begin with this. Okay? But I'm going to try and break it down for you guys. I'll show you how to go through and answer the questions based off of these things. But when we're dealing with concepts, it's a lot different than if we're dealing with a mathematical equation, right? The equation is just you plug in numbers and you go. For a concept, you have to make sure you understand what the world is asking, what the world the ideas come from, even to begin with. Okay? So just make sure you guys are spending the time with that. But the idea that we got to is that the quantum numbers, the 4 quantum numbers, are basically like the street address for where the electrons are going to live. Okay? If you know all 4 of those values, then you can figure out where an electron is. Now, why in the world would we care about that to begin with? Well, it's going to become really important, in the mystical future that I keep telling you guys about, that electrons are the things that do chemistry. Okay? bonds being broken, bonds being made, bonds being transferred. This is all dealing with electrons moving around. And if we say that electrons are moving around, then we have to know where they begin and where they end up, right? And so now we're going to the very basic idea of where the electrons begin, right? We're defining, given those four values, where the electrons start out, okay? Now, what we're practically going to do with this here is we're going to use that idea to build up how the periodic table is put together, and then relate this back to the idea of how do we know, or where do the similar properties of the elements come from. So if you remember, what we've talked about is that elements in the same family, the up and down, have similar properties, okay? So lithium and sodium, potassium, rubidium, right, all these are in the same family, they behave very similarly. And if building off the statement that I just made there, if the electrons are the things that do the chemistry, then if we have a way of explaining or describing the electrons, then that should help us explain why those properties are similar to begin with, okay? And we're going to relate this back to our oxidation states, and we're going to relate this back to our ionic charges, and all these kind of things that we've been talking about all along. And then once you guys have a good grasp on that, we'll throw it all to the wind and we'll say, here's something completely different, okay? So just when you think you have a good hold of it, then we'll talk about another type of charge, and then it'll get even more confusing and life sucks, right? No, I'm just kidding, it's not that bad, but we'll go through it. So anyway, hopefully you guys saw that the last lecture that we went through there, and that this isn't just a word salad up here for you guys, right? The S, the P, the D, and the F orbitals are defining the shapes. Okay, those shapes are going to show up at specific places in the periodic table. Okay, the electrons live in those orbitals, and the different shapes have different reactivities and all this kind of stuff that went along with that, right? The electron shell on the left-hand side there, the N, that's dealing with our principal quantum number. Remember that defined how big these orbitals are, okay? Our subshell there, that's the shape of the orbitals. How many orbitals there are, that's M sub L, right? And remember, M sub L is that tricky one where we don't care what the numbers are, we just care about how many numbers, okay?
Huh?
We don't care how many numbers there are, we just care how many numbers there are, okay? So, don't worry, we'll show it, we'll go through it again, but it's in the lecture here, right? That's okay, right? So, that's going to tell us how many of each subshell there are, right? How many S, how many P, how many D, how many F, G, etc. orbitals there are, okay? Now, this number here is kind of, I don't know, they're redundant in the sense of each orbital that exists can only ever fit 2 electrons in it. It doesn't matter what the size, the shape, or the whatever numbers are associated with it. Each orbital can only ever fit 2 electrons in it, okay? Yeah, what's up? What is an orbital? It's a region of space that defines a possibility or a probability where electrons exist, right? So that's going to be important because we're going to be dealing with the pairs of electrons, right? And so when we're talking about pairs, we're dealing with a set of electrons that live in a specific orbital, okay? Now, on the right-hand side here, the 2, the 8, and the 18, we're going to come back to that number again. That's going to help us just kind of build into the periodic table is what it is, okay? So anyway, that's just kind of the summary slide of the previous lecture there, so I just wanted to kind of pick up with that. All right, so now let's take a trip through the different types of orbitals, okay? So just the shapes and kind of what happens and what we should know about them and some of these kind of things, right? So when we're dealing with the S subshell there, we said that these are spherical, right? And that's mostly true. I'll show you where that's a line just a little bit, okay? But for our purposes, it's just fine to think of these as a nice sphere, and our electrons are living somewhere inside that sphere is what it is, okay? What defines an S orbital in terms of our quantum numbers? Remember, that's when our L is equal to 0. Now, if you go back in your notes, or if you take a look at the slides that I have for you there, L equals 0 is always a possibility, no matter what N is, okay? Remember the limits for L, right? I'm talking about the L at the top right-hand side there. The limits for L are 0 to n minus 1, okay? From 0 to n minus 1. The lowest n we can ever get is 1, right? So we will always have an s orbital available for us, okay? If we go here, take a look at how we kind of start to name our orbitals, or how we start to assign orbitals or think about orbitals, right? So when we talk about the different n levels, right, we call it our 1s orbital, where our 1 represents our principal quantum number, okay? So we have 1s, 2s, 3s, 4s, 5s, 6s, 7s, yada, 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 okay? So that number out in front there just tells us our principal quantum number, okay, our n. So what I'm going to ask you guys in just a little bit is say, where are the electrons in sulfur? Right? You guys are going to have to know your N, you're going to have to know your L, and then we'll kind of talk about the other values that go with that. Okay? So when I talk to you guys about the 3s orbital, the 3 just represents that principal quantum number, and the s represents the shape, or the L, right? The L quantum number. All right? As n gets bigger, the sphere gets bigger. Okay? Now, what does this practically mean? Okay, so let's think about this for just a second. Who cares that n gets bigger and that the sphere gets bigger? What's at the middle of that sphere?
The nucleus?
The nucleus. What's in a nucleus? Protons and neutrons, right? So at the middle of this, there's a tiny, tiny nucleus, relatively speaking, right? The nucleus is far, far smaller than the volume that's depicted by the orbitals, the orbital sizes, okay? So what is living in those orbitals? So the nucleus is at the middle of it. What's zooming around in those orbitals there? Electrons, okay? What charge does an electron have?
-1.
Negative, right? What charge is in the nucleus? Positive, right? So what practical, think about this for just a second, what practical implication does it have if I start to make larger and larger orbitals? Does my nucleus change size? No. But if I have some massive 7s orbital, what's happening to the electron in that 7s orbital? It's further away from the nucleus, right? And if an electron gets really, really, really far away from the nucleus, what happens? It leaves. It leaves, right? Yeah. There's nothing that's holding it to that atom. Okay? So if an electron decides to leave, it decides to transfer to something else, right? Then a reaction starts to happen. Maybe a redox reaction or something like that, right? So we're going to come back to this idea of that the size of the orbitals is going to be really darn important. Okay? So just hang on to that thought. We'll come back and we'll expand upon that idea. But remember, the bigger the orbital, that just means that the electrons are starting to get further away from the nucleus. Okay? Cool. In the book and in some of these other places, you'll talk about these, they have these two-dimensional graphs of the probabilities. Don't worry about that too much. There is a remember, this is a mathematical function that's represented graphically, right? If I gave you guys the correct formula and you guys plugged it into your calculators, you could sit there and graph the shape of these orbitals also, right? And then if you just take a two-dimensional slice of that, that's what these are here, right? So we just have distance and then probability, right? And then if we just translate that to three-dimensional space, then we actually get the shape of the orbitals itself, right? So it looks tricky, it's just, don't worry about that too much, right? If you guys are going on to some of the advanced chemistries, then we'll come back to these ideas here, right? But for now, it's just there to scare you guys, okay?
Oh.
I know, a graph, very scary. P orbitals, okay? That's when L is equal to 1, right? And we have 3 P orbitals for every L equal 1, right? Whenever we say that P orbitals exist, right, the implication is that all 3 of those orbitals exist also, okay? We can't just have one of those P orbitals exist by itself. If we are at L equal 1 subshell, then we have the Px, the Py, and the Pz always present, even if an electron isn't in them, okay? We'll talk about that in just a second also, how we start to fill things in, all right? But the idea that I want you guys to think about is if there are P orbitals We have all three of them, no matter whether they're fully occupied or half occupied or unoccupied. Okay? What's up?
Like that one on the left, that first one, it's one p orbital is two oval.
Yep. So, if we take a look at our 3p orbitals, we tend to say that they have a dumbbell shape. That's kind of the normal description that we give for it. That scatter graph on the left-hand side there might be a little bit of a better view of what's going on. So, if you take a look at that graph on the left-hand side there, you'll see that right in the middle of the graph, there's no dots at all, right? So that the scatter graph is a two-dimensional slice of one of these orbitals. So what's at the middle of one of these orbitals? Again, it's the nucleus, right? So what does this tell you? Can electrons exist at the nucleus? No. Well, that kind of makes sense. If they could exist at the nucleus, that's where they go, and then all existence would cease, right? Because all the electrons would cancel out with all the protons, and there'd be nothing, right?
Well, that's a scary thought.
it's an interesting thought.
When you get electrons left, they have the same mass.
No, it's all based off charge, right? They don't have the same mass, you're right, but the charges are the same. So here's the other tricky part of this. Where in that two-dimensional slice does the electron exist? Does it exist on the right-hand side or the left-hand side?
Both?
Both. Okay, how does it get from one side to the other?
Teleportation.
Basically, right? You guys see what I'm saying with this? I'm saying there's an area of zero probability in between these two lobes. Okay? Now, in our macro world, I can't get from one side of the room to the other without physically crossing that distance, right? But an electron can exist in basically both of these lobes, and it doesn't have to cross through the middle, right? It's very, very stupid. No, I'm just kidding, right? It's just so, it's completely different from the way that you and I see the universe, right? And if you think about this, this is why it took so long to kind of start to develop these things. Because they started to look at the mathematics and they're like, this doesn't make sense. How can things go from one side to the other without it physically crossing through there, right? And then we bring in this idea of quantum tunneling and all these kind of ideas, and it's actually really, really important that these exist in this way. When you guys get on to your later biological classes, you'll talk about the electron transport chain, and I think the current explanation is the electrons just pop from one side to the other, about 10 angstroms away, right? I might be wrong with some of those numbers. Maybe they've come up with a better theory at this point, but the last time I looked at it, electrons just kind of poof themselves where they need to be, right? Welcome to the quantum world is what it is. Now, how does that practically affect us here? Well, what I want you guys to think about is that the electrons just can't exist in these regions, okay? We don't have to sit here and look and worry about the mathematics about what happens in between there, because I don't even know if I could really explain it to you guys any better than I did, right? These are just areas of probabilities, and the electrons can exist somewhere in there is what it is, right? I don't think we'll ever really be able to visualize an electron itself, right? But we certainly have passive ways of doing it, right? Actually, fairly simple passive ways of doing it. But anyway, we have the px, the py, and the pz orbitals. Each one of those orbitals can hold 2 electrons, okay? So I want you guys to think here for just a second, this is important, okay? How many total electrons can fill a p subshell? 2 in each orbital. I have 3 orbitals, so a maximum of 6. You guys got it? Okay? So that's going to be important, so hang on to that thought, all right? Remember that, how do I know that I have 3 orbitals? Well, I get my 3 orbitals from my m sub l, okay? Remember, what are the limits for m sub l? They're from negative L to positive L. So from negative 1 to positive 1. Hence the minus 1 to 0 and the plus 1, okay? Does the minus 1, hang on just a second. Does the minus 1 represent anything to us, really? No. Does the 0 represent anything to us? No. Does the 1 represent anything to us? No. What is important is that I have 3 answers. 3 answers, and I have how many orbitals? 3. You guys get what I'm saying with this? Now, some books will say, oh, well, m sub l minus 1 represents the px orbital. Sure, if you want to think about it like that, that's fine. I would disagree with that, but whatever you guys need to kind of, get the concept in, okay? All I say is that I've got 3 answers and I've got 3 orbitals. That's the important part of it, okay? No one ever says, oh, this is the p minus 1 orbital. Okay, we call it the px, the py, and the pz, okay? What's up?
I know L is like, how, or the shape of it.
Yeah.
But what is L? Like, how do you-
What is
How
L?
do you know what L is? Like, M sub L, I don't know what that means.
So your question is, what does it represent, or where does it come
Well,
from?
like, okay, so, and I have it right here, principal quantum number, what is L?
What is L? L represents the subshell that we're in. So when you do these nice big complex equations, there's basically 4 values that fall out, n, m sub L, and m sub s. Excuse me, n, L, m sub L, and m sub s.
If I know what L, like, how do you know how to get L? What L you're in?
Based on, so yeah, that we'll get that from the periodic table, right? Yeah. So I'll kind of show you guys how we figured that out. But there's 2 ways of looking at this. If L equal 1, then we're in the p orbitals. If we're in the p orbitals, then L equal 1.
Okay, I didn't know if I missed something or, okay, I got it.
No, yeah, once I start to kind of visualize this for you guys here from the periodic table, it might make a little bit more sense then. Right now, it's kind of just all heady and out there, right?
Yes.
Okay, so px, py, pz, 3 orbitals, maximum of 6 electrons that can fit into that subshell there. Okay. All right, here's our d atomic orbitals. L equal to 2, right? If L equals 2, then my m sub L is -2, -1, 0, 1, and 2, right? So if L is 2, then m sub L can be -2 to +2. That's 5 values, so I have 5 orbitals, okay? If each one of those orbitals can hold 2 electrons, what's the maximum number of electrons I can fit into my d shell? 10, okay? Yeah. But if you take a look at something like the D here in the middle, right, the DYZ. The DYZ is basically just 2 p orbitals kind of smushed together, okay? And that's not coincidental. There's something we haven't talked about. I think the book mentions it a bit. There's the idea of radial nodes and planar nodes. And that's just, remember, a node is just where a function switches from one to the what's the word I'm looking for? It switches from negative to positive, right? And so there's a point where it goes through 0 is what it is, right? So a node is just a probability of 0 is what it means for us. Okay? We don't care about that, we're not gonna calculate it, that's all these kind of things, but there is a rhyme and a reason for why they have the shapes that they do is what it is, okay? The dx, d, dy, z, x squared minus blah, blah, blah. I don't need you guys to know those, right? Just I need you guys to know that there's 5 orbitals. They are distinct, they have unique orientations, right? They're either on the axes or off the axes, depending on which one it is. But remember the point that I'm trying to get across to you guys here at this level is that we can fit 2 electrons in each orbital, there's 5 of them, and they do have distinct orientations. And that does change the reactivity of our d orbitals quite a bit, okay? And it'll help us explain some of the things we've left out as we go through Gen Chem 1, right? And so we'll talk about that in just a little bit, okay? All right. Now we get into some of the fun ones that we don't ever talk about, boo, right? But our f orbitals, okay? Our f orbitals are mostly just kind of left, oh yeah, I'm sorry, what's up?
So like the 3 is like the N, right? Or what is the 3 for in front of all those?
Yeah, oh, yeah, sorry, yeah. So, that's a good point, right? So why did I call these a 3D and all that kind of stuff? So remember, if where's my pen, there it is, right? If L is equal to 2, what are my limits on L? L is always what? 0 to what?
2, 1, and negative
To n minus 1, right? So if n minus one, right, is equal to two, what's the lowest value of n I can have? Three, okay? So the lowest n value I can have for my d orbitals is gonna be three, okay? Because if I have n equal two, the max I can have is L equal one, right, which I can't access my d orbitals, okay? So the n in this case is just our principal quantum number, right?
So it could be four, like.
Could be, yep, but it can't be lower than three.
In this instance, like in this case, the L equals two is like one, it would tend to be two, or,
I'm sorry, ask your question one more time?
so, you're saying for this one, it can't be lower than three, right? But
Yes.
If the L wasn't equal to two, it was like one, could it end up being, it could be smaller, right?
If L is equal to one, then we're dealing with p orbitals,
Um,
right? The L defines whether we're the S, P, E, or F, right?
Okay.
The principal quantum number just defines, you know, basically what's accessible and how big our orbitals are. Okay. Our F atomic orbitals basically look like two sets of d orbitals kind of squished together. We add some more of these planes, or excuse me, these nodes that I talked about there. There's 7 d orbitals, but that's not necessarily true. There's actually different types of these orbitals that are called the cubic and the general set. Who cares, right? The point is, the F orbitals are just a continuation of the same ideas that we had for the S, the P, the D, and the F. What's interesting about the F orbitals is that they actually behave very differently from some of our other orbitals. There's similarities, right, but there's actually some very unique, let's say, reactivity that comes across with this, right? And remember, if we think about this for just a second, why might that be? Well, remember, each one of these orbitals, no matter what color I shade them, or how complex they might be, or whatever this is, right, there's only electrons living in those. But if electrons are living in different types of orbitals, it should make sense that they start to have unique reactivity that comes along with them, okay? What's up?
What's with the Saturn ring one?
This one?
Yeah,
What's with it?
yeah, like, all of the other orbitals are basically shaped like balloons or kidney beans or something.
Yeah,
That thing is continuous in
yep,
like a ring.
sure is.
Why?
Because that's one of the solutions to the equations that come out of this, right? I can't tell you why, I mean, you'd have to, you know, wait a couple of years and God will answer it for you. I really don't, I mean, that's the best I can tell you at this point. This is the, right, the graphical solution to one of the equations to solve out for what the orbitals look like. That's the best explanation I have for you.
Are there other ones that have even more rings?
Yeah, so if you went up to our G and our orbitals beyond F, then you probably end up having some different shapes of these also. Okay? Yep, it is interesting. But anyway, so unfortunately, our F orbitals are always the elements that you guys want to learn about. I'll show you what I mean with that in a little bit.
Radioactive?
Yeah, but we don't teach nuclear chemistry anymore, just because it kind of got dropped out of the national curriculum, right? So maybe in the future, if they bring it back in, you guys can sign up for more school, and then I can yammer on about that stuff with you guys. But yeah, what's up?
Okay, are they different colors? Because like the electron, if we were the very top left one, it only be the pink one or just the purple?
They're different shades because of whether it's a positive or negative solution at that point, right? We're just changing phases is what it is, right?
Okay.
What's up?
So for the, if they're like different shapes for positive and negative, for the.
They're not different shapes for the
Or not
positive.
shapes, shades, I mean.
That's just a visual representation, right?
So what's with the third color, the gray one in the bottom?
That's just that it's in the back.
Okay.
Yeah, otherwise it would overlap with the colors that are in the front and just be a giant mess,
Okay.
right? That's all it is. It's just, you know, we're trying to represent three-dimensional things on a two-dimensional plane, right? It's very challenging to do. Okay. So this is one of my favorite kind of posters / slides. This wasn't, I think I took this from a poster. This is the periodic table mapped with the orbitals, okay? Now, this is important for a couple of different things. So if you guys grab out your periodic tables and kind of hold it up and take a look at something, right, you'll see that the shape is not arbitrary, right? And you'll see that the shapes actually line up with specific orbitals that I have represented here, okay? And that's gonna be the important thing. Because what I'm gonna start to talk about is the idea of where different blocks are on the periodic table. The S block, the D block, the P block, and the F block, okay? And where we're gonna build with this is that as we take a walk through the garden of the periodic table, we're gonna start to fill electrons into specific orbitals in that block, okay? So it's important to recognize how we can break apart the periodic table, okay? So on the left-hand side here, where we have our alkaline and our alkaline earth, right? Your sodium, potassiums, your calcium, berylliums, all those, right? That's gonna be my S block, okay? How do you know that it's S block? Well, we see our spherical shaped orbitals here. Right now, these are cut in half, okay? To show you guys that the orbitals are actually a little bit more complex than we might imagine, okay? We don't talk about this, but there are layers to the different orbitals themselves. It's not a continuous sphere, unless they're at the top there in the 1s orbital. Other than that, there's different phases that exist in them, okay?
So they're like over.
Yep, they have layers, just like onions. That's true. Right, so on the left-hand side is our S block. On the right-hand side is our P block, right? So starting from boron and aluminum and gallium all the way over, right, to our noble gases. That's our P block. In between there, where our transition metals are, is where our D block is. So starting with scandium all the way over to zinc. And down at the bottom, let's see, I think, where's the one that I gave you guys? Yeah, okay, so the one at the bottom there, you guys start out with lanthanum and actinium there, La and AC. That's technically part of the D block. So starting with cerium, Ce, and moving over, that's your F block there. Now, why in the world would they bring lanthanum, all that stuff down there? Well, don't worry about that too much, but there is a rhyme and a reason for this, right? But basically our F block is down there at the bottom is what it is. Okay? So, who cares? What are we gonna do with this? Well, now the question is gonna become, how do we know where electrons are in something like boron? Okay? So we're gonna have to know where boron is on the periodic table, and we're gonna have to know the different blocks that make up the periodic table. And then we're gonna have to know how we can systematically add electrons to get to the electrons that are in boron, okay? What's that?
So 7s is like the most reactive, right?
In the s orbitals, sure.
Well, like that would be francine, right?
Mm-hmm.
So higher number means higher reactivity, right?
Not necessarily. I know what you're asking at the moment, and I'll say yes, but you'll see where that's not necessarily true. I would say the highest numbers are the ones that react in a particular atom. But there's actually different types of electrons that we'll talk about that will kind of make that distinction.
So do simpler shapes make it easier for electrons to be exchanged? While more complex shapes are.
That's an interesting question. I'm gonna say, I don't know what you mean by simpler.
Like, okay, the sphere is pretty simple. It only has essentially like one surface area for the entire world in a way.
So let me answer the question this way. For a reaction to happen, right? We'll talk about this in a little bit, but there has to be something called, basically we work out something called collision theory.
Okay.
Which means for a reaction to happen, the right atoms have to come together at the right time, at the right speed, at the right angle, for there to be an overlap with the orbitals and the electrons to move around, okay? So you might be able to make the argument that because we have a sphere, we take the angular component out of this, right? And that might make it quicker, but to be honest, I don't know, I never thought about it from that perspective. I would, my instinct is to say, no, it doesn't make a difference, but it could be, I don't know, I've never thought about it, good question. Right? But we'll talk a little bit more about collision theory and just kind of, that'll make more sense when I talk about it. Okay. You snapping at
Oh,
me?
no, I don't.
Come on, old man, get to the point. Alright. So just kind of going back here. So we're gonna take this idea here that we kind of built with the Bohr model there and try and expand that to all the other elements in the periodic table as best we can. Okay. Now, obviously, we mentioned that there are some limitations with the Bohr model there, and those are obviously true, but the ideas that we kind of expressed in here are good for, let's call them back of the envelope approximations for the other elements in the periodic table, okay? So, what do I mean with that? The lowest energy orbital that we're going to run into is our 1s orbital, okay? Now, that should make sense in a couple of ways. Because if we start to take a look at the periodic table, and what we just talked about is our S block, right, which is our left-hand side, where, what is the first element that we run into in our S block? Hydrogen, okay, so it's got one electron, that one electron is going to be living in our 1s orbital, okay?
Boring life.
I wouldn't say that, well, hydrogen's pretty darn important to everything in the universe, right? But fair enough, right? It's a pretty boring looking orbital, right? It's just in a sphere, right? Now, a thing to think about, I just find it, a thing to think about is electrons are like me. I'll use myself as an example, okay? Electrons are like me. Given my, we'll call it the sin nature of the flesh, right, as the Bible puts it. Given my proclivities, I'd love to just be lazy and kick back on the beach and just kind of do nothing all day long, right? I'd like to be lazy, okay? What that means is I like to go to the lowest energy state that I can, okay? And that's the reason why you guys came in this room. And instead of holding your notebooks and walking in circles while you're listening to the lecture, you guys came in and sat down, right? Why? Well, because, that's the lower energy state, right? So the electrons are going to work the same way. When we start to put electrons into atoms, aka when we start to put electrons into orbitals, we're going to have to find the lowest energy orbital for it to go into, right? So how are we going to know when things are low energy? Well, one of the indications is our principal quantum number n. The lower the n, the lower the energy, okay? That doesn't necessarily mean that it's more or less reactive. I'm just saying that's the lowest energy that's available, okay? Again, think about this. How many electrons can fit into a single orbital maximum? 2, right? So once we put 2 electrons into a orbital, we have to go find a new one for them to go into. Got it? Just like most of you guys only have one roommate, right? And that's probably too many in some cases, right?
I have
You're pretty, I'm sorry. It gets old fast, but, right? So the same idea here. Now if we take our orbitals and our principal quantum numbers and start to represent them in a, let's say, less graphical manner than the previous slide showed, right, what we can start to see is where electrons start to fall out in terms of energy levels here, okay? Once we're done with our 1s orbital, we hop up to our 2s. That's our next available orbital set, okay? Once we fill our 2s, we can go to our 2p. Now, what do you guys notice about our p orbitals here? They're all at the same energy level. So the 2px, the 2py, and the 2pz are all of equivalent energy. And we just happen to use the term degenerate for that, okay? We would say there are degenerate orbitals. So when I'm filling electrons into my p orbital set, we're going to have to approach this a little bit differently. We'll talk about that in just a minute, okay? For my 2p, I go to my 3s, then my 3p, I go to my 4s, then I fill in my 3d, then my 4p. So you guys will start to see there's a pattern that starts to come out from this, okay? It's almost as if these orbitals begin to repeat themselves or align themselves in some kind of periodic fashion. I wonder if we could put this into some kind of table format or something. Right? But we'll talk about, or just something to start to pay attention to, the 3D is technically above energy than the 4S is, despite it being a principal quantum number of 3. Because if it was easy, right, then we couldn't make you guys miss questions on exams, right? That's unfortunate. What's up?
So the difference between like 3D and 4D is,
Yeah.
I just wanna clarify, they have the same amount of electrons, right? Although it's a bigger.
They in theory can fit the same amount of electrons.
Okay. It's a bigger volume.
Yes.
But it still has the same, like 2%.
Yep.
Right?
Yep. That's it. So how do we start to fill electrons into these things? Well, we're going to have to use Hund's rule, and that says the most stable arrangement of an electron in the same subshell has the maximum number of unpaired electrons, all with the same spin. Okay, here's what that means. It means when you're filling in electrons into degenerate orbital sets, okay, you put them all in by themselves before you come back and pair them up, okay? So you give everybody their own apartment, and then you assign roommates, okay? That's what it means. Now that makes sense, doesn't it? Doesn't it? What charge do electrons have? Negative. If you're a roommate, right, are you guys in close contact with each other?
Yep.
Yeah? Can you guys sometimes get on each other's nerves?
Yep.
Yeah. Okay, would you rather be living alone sometimes? Yeah, it's the same idea with electrons, okay? If you think about it, there's a repulsion, right? If they're in the same orbital, these things are by definition closer to each other, right? They're in the same probabilistic region. And so there is repulsion between having electrons in the same orbital, right? But if we can spread them out between different degenerate orbitals, one in the px, one in the py, and one in the pz, that's going to be a more favorable situation for them, okay? Rather than cramming them all together into one set of orbitals, or excuse me, into one orbital itself, okay? So how does that look for us? There it is, okay? So, I'm just kind of drawing the idea here from the previous, let's see, what color was it? Blue, okay? So if I'm taking a look at my, my 2p set from that previous slide there, right? I have my px, my py, and my pz, okay? If I am asked to start to fill electrons into these orbital sets, just put them all separate before you come back, okay? Now, the way we represent electrons in terms of how we fill them in are either by, usually by arrows, and the arrows are either going to be pointing up or pointing down. And remember, the last quantum number that we talk about is m sub s, which just means spin up or spin down, spin 1/2 or spin minus 1/2, okay? So if I'm filling electrons into here, if I have 3 electrons to fit into my 2p orbitals, that's the way I would put them, okay? That's what Hund's rule says. Once I have to add more than 3, then I come back and we start to pair them up, okay? Up to a maximum of 6. That's all it means.
What if you have an odd number, like 4?
Ah. No, I know what that.
Yeah.
What if a number not divisible by 3 directly, right? That's it, right?
Oh, that's it for arrows? That was an error.
Yeah.
Okay.
Yeah, sorry, I'm yeah. Ooh. It's a roommate that ate all their neighbor's food. Okay. So, if I just have 2 electrons to fill in, okay? Here's the thing that might, I don't know, maybe tricky or annoying or whatever you want to say with it. That's a perfectly acceptable way of filling in electrons, okay? And that would be just as equal as saying this, okay? All the rule says is, don't pair them up until you have to. Remember, our assumption is that all those orbitals are at the same level. So does it matter that I put one in the px and one in the py, or one in the px and one in the pz? The answer is no, right? By convention, we just fill them in left to right. Why do we do that? Because we write left to right, right? Okay, so but does it really matter? No, okay, it doesn't. As long as you don't pair them up until you have to, okay? Maybe I didn't put it in my, slides, but this is a big no-no also, okay? The Pauli exclusion principle says that we can only have one unique set of quantum numbers per electron, okay? So what I mean with this is, right, we have our N, we have our L, this is represented by some M sub L, we have to have a distinct M sub S also. You can't have two spin up, you can't have two spin down, okay, because those would have identical quantum numbers that are associated with them. That doesn't exist, okay? Yeah?
Doesn't your thing say that unpaired spins all go up or down?
Yeah, typically. We typically start with spin up by convention again. We don't, technically if you have one spin up and one spin down in separate orbitals, that's actually slightly higher in energy is what it is. Now, why is that, or when do you learn about that? Come take one of my module classes, I'll talk to you guys about that then, right?
So could you take that red one, reverse it, and put it in Y, and have that work?
Sure, yeah. That's what, but my point here was just, you just can't have two of the same spins in an orbital is all. What's up?
What is this spin? How do you know like if it's up or down or side?
That's just by convention. They're just moving in different directions is what it is, right? They're spinning, right? There's no up or down necessarily for an electron, right? They're just spinning in opposite directions.
Does it matter which way I put it? Like if I have three of them, and I want to put one of them down, like. what is-
Technically,
What's
no.
the point?
What's the point?
And, yeah, like, how do I know whether to put,
We usually start with spin up, is what it is.
okay.
But if you did all spin
Oh, if I
down,
had six, I'd put one up, one down. and-
Correct.
Okay.
yeah, that's the first thing that I showed you guys there, right?
Yeah.
We do all the same spin, then come back and do all the opposite spin. Cool. Alright. So if we take our periodic table and kind of expand it out, if you guys have ever wondered why we block or why we drop that F block underneath there, it's just because it's nicer to fit on a single piece of paper is really what it is. The way we fill in electrons is like this, okay? This is what the slide is showing you. We always start at the top left-hand side and we move left to right, okay? So as we start to fill electrons into our orbitals, into our shells, we basically take a walk from the top left-hand side all the way through to what we need, is what it is, okay? Now you'll note that I have a note, or you'll see that I have a note here for you guys about the F and the D blocks, okay? And I'll put this, I'll let you know what I mean here in just a second, okay? So let us talk real quick about how we can write our electron configurations. And then we'll start to do some examples, because I'm tired of talking, is what it is, right? So how do we start to write our electron configurations? There's two ways. We have the expanded and we have the condensed. We're pretty much only going to stick with the condensed is what it is, okay? But remember, the expanded is there to kind of remind you guys that each orbital can only fit 2 electrons. But an entire block, right, we take into account that all the orbitals are there, okay? So if I ask you guys the electron configuration of hydrogen, hydrogen's at the top left-hand side, it's in the S block of the periodic table. We start at the lowest energy orbital available, that would be our 1s, and we would say that our electron configuration is 1s1. Not too bad, right? Now, how many electrons can fit in a single s orbital? 2. So for helium, we could fit our second electron into that same 1s orbit. And we would say helium has electron configuration of 1s2. Good? If we move our way to lithium, we can fit 2 of our electrons into the 1s, and our next one goes into the 2s. We drop down to the next period and start to fill our way from left to right also. Okay? And et cetera, et cetera, et cetera, et cetera. You'll see that our 1s and our 2s's are always going to be filled, and as we continue to grow this out, right, we always start with our 1s. Once we're done with our 1s, we go to our 2s. Once we're done with the 2s, we go to the 2p. From the 2p, we would go to the 3s, and we'll talk about this pattern in just a second. What's up?
How can you have S and P in the same atom?
How?
Like, aren't each of them supposed, like, so the P and S, they represent, L, right? But they're like the value for L decided the
It
orbital.
decides which orbitals we're looking at. I didn't say that they're exclusive, right? Technically speaking, every orbital is available to every atom from hydrogen. Just energetically, they're not accessible. And you're never gonna see d orbitals on the hydrogen is what it is. Okay? So all the orbitals are there just as we start to add protons to it, right? These just become more accessible to the electrons, and then we can start to fill them. Right? If you want to think of it like urban crawl or urban expansion,
So do
right?
they overlap?
No, they're discrete. They're discrete areas of probability.
Okay, thanks.
Mm-hmm.
What does discrete mean?
They're distinct to themselves. Yeah. All right. So here's the last thing before we go into a little bit of examples. There's these different ways of what we're going to be doing, or what I'm going to show you guys. I don't know, some of these, whenever this, is maybe simpler, but then you have to kind of write it out all the time. I'm going to show you guys how to do this using the periodic table, is what it is, okay? Because the periodic table is always going to be there. It doesn't involve me writing things down. I need to memorize things, but that's just me. Whatever you guys need to do to be successful, go for it, okay? But this is all based on what's known as the Aufbau principle there. Right? German Aufbau is just German for it builds upon, right? So what we mean with this is that whenever we add electrons, we're going to add it on top of everything that was there to begin with. We start at the bottom, we work our way up. That's all it is. Okay? Cool. So now let's pop over to our periodic table. There it is. Okay. And what we need to do when we're starting to do electron configurations is number on the left-hand side. What I do is 1, 2, 3, 4, 5, 6, 7. Okay? In green here, this is my S block. Purple, this is my D block. Put that right here, S, D, yellow. This is my E block. Huh? No, yes, it's in the S, not the P, yeah. And down here in red, I'm not gonna box it in, but that's my F. Okay?
And that includes lithium and
Technically, these are here.
okay, so they would be in D1.
Yeah, it's a little bit weird. Okay, so once we got that kind of marked out and numbered, then we can start to do electron configurations. So, typical question, what's the electron configuration for carbon? Okay? Now, what we do is we just take a walk through the periodic table. We start at the top left-hand side and we keep adding electrons and walking through until we get to the atom that we want. What's up?
So it would be 1s, 2s, 2p?
We'll get there, yeah. But we have to say how many electrons there are, right?
6.
Well, where are they? What orbitals, right?
Oh.
So what we do, we start over at hydrogen, right? When we're building our way to carbon, we start at hydrogen and we start to walk step by step by step. We follow the numbers in the periodic table, right? Hydrogen is 1, helium is 2, lithium is 3, beryllium, right? 4, 5, 6. Remember, those are our atomic numbers. They represent how many protons there are. But if we know how many protons there are, it also tells us what? How many electrons there are. You guys with me on this? So we have to account for all 6 of the electrons in carbon, right? So your answer better have 6 electrons accounted for. So let's do it, right? We've got all these pretty colors. We start out in hydrogen, so that's our 1s orbital is where we begin, okay? I'm gonna move down here. Oh, I can't, so I'll just do this. And that's not gonna help me at all. Perfect, just what I wanted. I didn't bring my pointer with me today. We don't have a yardstick or anything for me. Nuts. All right, anyway, that's okay, so once we're done with hydrogen, we're gonna take a step over to helium. Now think about this for just a second, right? If I'm in hydrogen, I have 1 electron that goes into there. I can fit 2 electrons into my s orbital cell. So 1s1 is hydrogen, 1s2 is over at our buddy helium, right? So we have 1s2. From helium, we step down to lithium, right? So now we're done with our 1, so we're back to our 2 and our s, okay? Lithium would be 1s2, 2s1. Beryllium would be 1s2,
2s2.
2s2. So if we're at beryllium, we hop across that gap to get to our p block there, okay? Beryllium, we hop across to our p block boron. So we are still at 2 here, okay? 2 p, right? And then we just say how many electrons in our p block there. 2p1, 2p, oops, that should be a black. 2p, 2.
Hold on. Wait, that adds up to 6.
Yes, it does.
For boron.
We're in carbon, right? I went ahead and went to carbon.
Oh, you said boron, okay.
Well, no, he said he goes from beryllium.
Yeah, from beryllium to boron, then to carbon, where you hop over that block, yeah.
Okay.
You guys with me on this?
Yeah.
Not too bad, right? Everything's gonna start out the same way, 1s2, 2s2, blah, 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 right? This is just a repeating pattern of things, okay? If you mark off your periodic table, if you do your numbers here, that's what's gonna help you guys out with that, right? Good? So let's go look at some of the exceptions then, maybe. Okay? So let's take a look at our buddy titanium.
Yay.
A crowd favorite, apparently.
Just kidding.
Woo, titanium. So, start it the same way. Whenever you walk through the periodic table, you start at hydrogen, and you systematically work your way up, right? So 1, I'm not gonna switch colors, hopefully you guys can, that'll take 30 years for me to get there, right? So 1s2, we're over at our buddy helium, right? We hop down to lithium and beryllium, 2s2. We hop across to boron, 2p, 1, 2, 3, 4, 5, 6, right? 2p, 6. Does that make sense? Where does that 6 come from? We have 3p orbitals, and how many electrons can fit into 3 orbitals? 2 each, so a maximum of 6. You guys with me? Right? So now we're over here at neon. Neon, we hop down to sodium, so now we're 3s2, right? Sodium, magnesium, we hop over to aluminum, 3p6, okay? So now we're over here at argon. Hop down to 4s2, things take a turn.
Now we have D's.
3d2,
Wow.
okay? So remember in one of the slides I said pay attention, I said it takes a step down, right? This is what I mean. Take your number here, and when we hit the D block, it's this minus 1 is what we're gonna run into, okay? So when you number on the left-hand side here, right, this is our 4s, our first D orbital we encounter is our 3D orbital, okay? That's the lowest quantum number we can give to a D orbital. Because D is equal to L, a D orbital is defined by L equal 2. The lowest N we can have for L equal 2 is 3, okay? Other than that, everything else is kind of the same, right? So the electron configuration for titanium would be that guy there. Okay. So, oh yeah, what's up?
Okay, so for like, when you're like drawing like a picture of that, right, and you like have the elements right kind of, you put the dots everywhere. Is that symbolic of the shape of it? Like 2 dots on the top, 2 dots on the bottom. Is that like the shape of it where you're putting the electrons?
Yeah, kind of. Like I said, it's just a convention, but we have to talk about what kind of electron is represented in that. So we'll talk about that in chapter 7 and 8. So we haven't quite gotten there yet. Okay? So here's the point, real quick, before you guys start packing up. Okay? If I asked you guys, okay, write the electron configuration for bismuth, right? You guys would say, right? Right? There's no way I'm going to spend 20 minutes of my life, 1s1, 1s2, right? It would take forever to get there. And, as I admitted earlier, okay, us chemists, no, we're calorically efficient, okay? So, we don't call ourselves lazy, don't put that on your resume, say you're calorie efficient, okay? That sounds better, right? So we're gonna learn a way for how we can shorthand some of these things here, okay? And that's also gonna help us lead into the next idea of what different types of electrons there are, okay? But it would be good practice for you guys to do the longhand for some of these over here, just to take an idea of how to walk through the periodic tables a little bit. Right? Very common question on maybe exams or quizzes. All right, I'll see you guys on Friday. Unless the apocalypse happens or something. Okay? No.